Okay, we continue with hardware platforms. So we now have an idea about the computational attributes. I mean, that dimension. What is power efficiency? What is computational power, raw power? Or what is stability? Now having an idea about these concepts, if we had an idea about the architecture or different properties of different hardware platforms used for deep learning, we can compare them. And if we can compare them with these dimensions, we can have a systems engineering perspective to decide which embedded platform to use and when to use it in which application. And we're going to cover a number of platforms. You know, the embedded world is changing at a fascinating speed. Every day a new solution comes to the market for any application, not only for deep learning, for every application. It's changing for the last 30 years. The embedded world, the chips, those systems, microsystems are evolving at a tremendous speed. And now we have mainly a number of platforms we can use for deep learning, which are the CPUs, GPUs, TPUs, FPGAs, and system-on-chips, SoCs. Okay. And as I told you, since this is a systems engineering problem, we are going to compare these systems in these dimensions. Okay, machine learning is by definition is a set of algorithms. It can be implemented on anything that we can compute. Well, wonderful. If you can do computation on it, since this is an algorithm, you can just apply it. We will now review main technologies for this purpose regarding their strengths and weaknesses for implementing deep learning systems. And while we are doing it, as I told you, we are going to cover these dimensions, algorithmic details and embedded concepts. But we are not going to cover these much. We are going to cover them slightly, but not much, because this is more like engineering management, as I told you, and it is beyond the scope of this course. Okay. We start with CPUs. Wonderful. Central processing units are the traditional sequential processors for general purpose applications, guys. Once upon a time, there was only CPUs, nothing else. We had only CPUs. Everything was CPUs. Like when I was a child, when you said a computer, it was a CPU. All other devices like GPUs, they were called coprocessors. Okay, what is the good side of using a CPU? You can find them almost anywhere. So you're going to implement a deep learning system to an existing system. Well, rest assured that it is a CPU, so you can implement it if you're going to implement it to a CPU. They are very flexible because that was the idea. When first CPUs were created, they were all-purpose devices. That's why they were designed flexible. They are easy to use devices, because almost all programming languages can be compiled to their machine instructions. When a CPU is created, the first thing done is people write compilers to it for different languages. So you can use any programming language. Imagine you can, whatever programming language you know, you can implement it to CPUs. That's a very important advantage. And in addition, when you're implementing it, you don't want to just explore America again. Just you can use ready-to-use libraries. So various integrated development environments, IDEs, and machine learning libraries exist for CPUs. So whatever language you're using, whatever library you want to use, if you're using a CPU, go ahead. Very, very big advantage. And in order to implement a simple networks, like I said, AlexNet, or I don't know, like VGG is also simple, on a CPU, almost no design effort is needed. Well, provided that the extent of the available free libraries or reusable codes, well, if you're experienced programmer, and if you have access to these codes, it will take a couple of hours to implement it. So design time is very also short for CPUs. So let's try to understand the architecture. Well, if you've taken a microprocessors course, you know the architecture of a CPU. It's quite straightforward. Their processing architecture usually includes single or multi-core microcontroller units. So you have microcontroller units, each unit having some arithmetic logic instructions and control units. And they access a memory, single core or 8 cores or 4 cores. Usually not more than 8 cores. I've seen 16 cores, but no more than that. So you have a number of cores, and they are doing the operations in parallel for you. What is more, and what is more important is, most high-level processors have the so-called coprocessors for a specific purpose. So for scientific calculations, you need very high precision, floating point or double point precision. Then you need a coprocessor inside your processor. It is specifically designed to do that job, to calculate floating point operations. Actually, GPUs and all other graphical processing units were once coprocessors as well. They've become processors on their own within their evolution in time because graphics became very important, but floating point operations are still coprocessing operations, and it is inside the processor. So inside this processor, some part of it architecturally is a coprocessor for floating point. So floating point units provide fast scientific calculation with the expense of higher power requirements. So you spend more power, but you can get more operation. So they are like the performance power trade for CPUs. So imagine you are going to use a CPU for an embedded deep learning application, and well, okay, you can use a CPU. Well, you have power. It is not flying in the sky, so you can get power. Then use your coprocessor. Well, if you don't have much power, then implement your system in integer precision, quantize it using post-quantization techniques or quantization over training, and don't use the coprocessor, then you will spend less power. That's what we mean by performance power trade of device for CPUs. Okay, and as I told you, they are very flexible. They can make interfaces with almost everything. Those interfaces we have in embedded systems, we also call them peripherals. So in terms of peripherals, CPUs are very versatile and easygoing. They can just communicate with anything because they were there before everything, and so all protocols, existing protocols, you can apply them to. So wide choice of analog or digital peripherals exists for different models. In addition, microcontroller units include digital bus interfaces. So they're very fast information in and out can be mapped to these devices like shared memories. You can map their buses to shared memories, and you can access memories very fastly. So in terms of accessing memories, peripherals, or flexibility to different environments, CPUs are fantastic because they have been always there for decades. So their architecture is designed for multitasking in operating systems. So because your microprocessor, you're watching this video in a system, your laptop or desktop, your tablet or your cell phone, whatever, it's using this microprocessor, and it's doing a multitasking. You're having messages from another app, and so they are designed for multitasking and for running operating systems. It's something good because it makes you, as the coder or designer, comfortable. You can design many things on top of each other. They are designed for that purpose, but this is also a disadvantage, which I will talk in a couple of minutes now. And nevertheless, all aforementioned capabilities and versatility adds high overhead. So in order to be able to do this, to become this flexible, well, you pay a price. What is this? CPUs are optimized for sequential processing with limited parallelism. So they don't do parallelism, they do sequential processing. They do multitasking by cutting jobs into slices. So this makes them slow when it comes to more repeating operations, just like calculating the output of convolutional layers. So the biggest weakness for deep learning is their raw computational power. They are not specifically designed to kill performance, to have a killer performance. They are designed to do tasks sequentially on top of each other in a multitasking manner, properly and stably, and they do it fantastically. They can communicate with any environment, but when you say only do this operation, nothing else, very fast, they are not designed for it. That's their biggest drawback. That's why, to do that one single operation properly, we use different architectures like GPUs, TPUs, FPGAs, which we will continue now.